Hello everyone. Today we'll discuss a recent paper called PnG BERT, Augmented BERT on Phonemes and Graphemes for Neural TTS. The authors of the papers are Ye Jia, Zen Heiga, Shen, Zhang, and Yonghui Wu. This paper is coming from Google Research. The tutorial overview is as follows. First, we'll see the introduction of the paper. Then we will see what is PnG BERT and how it is used for text-to-speech application. Then we'll see experiments, and finally we'll see the results. So what is PnG BERTs? PnG stands for Phoneme and Graphemes BERT, or PnG BERT stands for Phoneme and Grapheme BERTs. So the idea here is to use or to leverage both phoneme and graphemes in transformer network, or also known as not exactly BERT. BERT is a variation of transformers. So the idea is to leverage both phonemes and graphemes in BERT setting for text-to-speech application. If you are in text-to-speech domain, or if you are working in text-to-speech domain, you may know that text-to-speech usually will have a sort of an encoder which takes some form of text, which could be grapheme sequence, such as, for example, let's say a welcome sequence of letters, English letters, or sequence of phonemes, which corresponds to this word welcome, for example, right? And the phonemes are like IPA symbols, whereas graphemes are alphabets or ASCII characters. And so once you consume, or once you feed the input to the TTS engine or the encoder, so the encoder will take this sequence of sequence of characters, and probably use some sort of embeddings, and then uses some encoder layers, could be a convolution encoder or could be RNN encoders, and then it generates something called spectrogram or MEL spectrogram, which is sequence of feature vectors. And these sequence of feature vectors are fed into something called ocoder, which generates the one-dimensional raw audio signal which we can listen. Right, so that is the whole setting of the TTS engine. Some people have tried to build end-to-end TTS engine, and so on. There are variety of variety of text-to-speech models and algorithms available, and this is a very well-known problem. People have been trying to solve this problem since 1990s. And Zen Heiga is one of the author in this paper. As a matter of fact, he has worked in this field for a very long time. And so in this paper, so the idea is to use BERT-like setting, which is using something called masked language modeling criteria with transformers for text-to-speach application. And one good thing about using BERT is you can pre-train it on large amount of text data, and then you can fine-tune it for other downstream such tasks. In case of NLP, people have used BERT left and right for many applications, like NLP application. But the first time I think, in case of speech or in text to speech, BERT is not experimented for text to speech application. And this paper shows how do we pre-train BERT on large amount of text data, and then we can simply attach it as one of the component in this text to speech, or an encoder in this text to speech, and then you can simply fine tune this whole model end to end for TTS application, and that seems to perform better. Like I said, so this model is augmented from the original BERT model. Like I said, it's a BERT model which has a sequence of transformer layers with masked language modeling training criteria, and the model uses both phonemes and grapheme representation, unlike in case of BERT, which uses only graphemes or subwords. This paper uses, or this model uses, both phonemes and grapheme representations from the input text, and we'll see how those are generated and how those are fed as input to the model in the coming slides. And along with that, they also use word level information or word level alignment between the graphemes, right? So, for example, if let me explain that word level alignment anyway in the coming slide. It's a part of the model architecture, right? So there is word level information provided to the model along with the tokens, which are obviously the phonemes and graphemes. and you have the position embeddings and so on. So with those, you can simply pre-train your BERT model with large amount of text data, and then you can simply attach this encoder as a part of this TTS engine and to any TTS engine. As a matter of fact, like if you have like attention based tachotron model or tachotron 2, or you can go with glow TTS. There are variety of TTS engines available. You can simply plug this as a part of the encoder, and then the decoder will generate the spectrogram for you or MEL spectrogram for you, and then you can feed it to the vocoder to generate the audio, right? So that's how it is done. And one amazing thing about this paper is you will get the performance is same as the humans, right? So basically it is measured with something called MOS score, MOS score, mean opinion score. So that score is similar to the humans MOS score. So we'll see that results in the coming slides. So we'll understand this PnG BERT um, in this fashion. First, we'll look at the PnG BERT architecture. Then we'll see what BERT is. I think many people will already know what BERT is, but I'll just give you a brief overview for the people who don't know. And then we'll see how input data is represented for this BERT model. And then we'll see how pre-training is done and how fine-tuning is done later. Okay, so this diagram is kind of familiar to many people because NLP is revolutionized by this model. Um, so in case of BERT, the main component of BERT is the transformer and the masked language modeling criteria. And they also have a few other criteria such as classification objectives and so on. So the way the BERT model is trained is a little bit different to what these guys are doing. So in case of BERT, they use two different objectives. One is the MLM objectives, which is the masked language modeling objective. So the idea is to simply predict the words which are masked in the input, and second is to predict whether the sentence whether the sentence next to the current sentence is actually the continuous or if it is taken from completely random sequence. So so but in this case they are not using this objective, at least what I have seen in the paper. So they are only using this MLM objective. So the training goes as follows. So first you have, let's say, few words, right? So let's say I am going to school, or let's say hello world, right? So you can generate, let's just form it like this. So you have input, which is, let's say, two words, right? Hello world, right? And you can already get phoneme sequence from this. So instead of taking characters, you can generate subwords, right? Let's say W1, W2, and W3, right? So the subwords are generated using, I mean, there are many toolkits which are like say a sentence CPs and so on. There are toolkits available to generate the word tokens or subword tokens, right? So assume you get this G1, G2, Gn, right? And to get P1, P2, Pn, so P1, P2, Pn are the phonemes correspondence of the sentence hello world, right? So how do you get that? So you can use something called G2P, so the grapheme to phoneme converter, which are sort of, I mean, there are many varieties of grapheme to phoneme models available. There are FST based ones, and there are neural network based ones. And in simple case, just assume we have some sort of encoder decoder architecture where you feed the graphemes in one end and it can generate the phonemes in another end, right? So then you will get the P1, P2, and so on, Pn, and the subwords are called G1, G2, and Gn, right? Now, what you can do is you can just concatenate them with a separate sep token, and then you will get your tokens, right? Now, that is the token part. Then you can also provide information about the segments, because we know that this is segment A, which is the phoneme segment, and this is grapheme segment. And you can also provide the word level information, which is very important because the paper, in the end, they have done some ablation studies that if you provide word information, the model works really well. If you don't, then the model performs poorly. You'll see that. So the word positions, you can simply provide word positions as sort of an embeddings, just like positional embeddings for tokens, right? And obviously you have the token position just like I said. So you have token positions, which are the positional embeddings of the tokens, and then you have word positions, and then you have segment information, and then you have the tokens as tokens itself, right? And then you can simply mask these two. I mean, you can simply mask some of the words in this segment, and then ask the transformer model to predict those segments, or predict those parts of the input, right? Using masked language modeling objective, right? So that's how the pre-training of BERT is done. This is like a very standard thing. And for fine tuning, what you can do is, you can see, once you train this model, you can take the transformer and then just plug it to the encoder part of any TTS model. So in TTS, you have these attention based models and duration based models. Like attention based ones are this tachotron and tachotron 2 and so on. And you have this duration based model, which is the paper called, which is, I mean, there are many paper. There is one paper called NAT, non-autoregressive transformer. So that model is kind of a duration. It's called duration-based sampler, upsampler model, and those you can replace the encoder with this transformer encoder, and then the decoder will be as it is, and the decoder will generate the spectrogram for you, or waveform, either way. So if it generates spectrogram, you can simply plug it to the vocoder, and if it is generates waveform, that's good because you already have the waveform. And then you can train this model end to end, and then you have your TTS engine. Unlike, I mean, instead of fine tuning the whole model, you can limit the layers you want to fine tune, because these models, the transformer models, if you're training on large amount of text data, those models have to be like larger, like the bigger, deeper models, right? So you don't want to fine tune the whole model for TTS, because for TTS you will have limited data. For example, let's say 30 or 40 hours of audio data, whereas in case of pre-training, you will get enormous amount of text data from web, and uh, and that's why the model has to be deep, right? So this is the whole architecture. And like I said, for the input representations, you have the tokens itself, and then you have segment information, and you have word positions, and then you have the tokens position, which are the positional embeddings, right? So like I said, positions are very important in this case. I'll tell you why in the coming slide, like in the Z section, right? And that is the input representation. And as I said, for the pre-training, you will train the model with masked language modeling criteria, and then you have the, like I said, masking should be applied at word level, not at token level. And then both phonemes and grapheme, for both phoneme sentence and grapheme sentence, 12% of the random words are replaced by mask tokens, right? And the remaining 1.5% of the are replaced by random words, and then again 1.5% of them are replaced by random graphemes, right? Sorry, kept both graphemes and phonemes of another 1.5% random words are kept unchanged. Okay, right? And MLM loss is computed only on the tokens which correspond to this 15% of the words, right? Not on the full full words, full sentence. And for the fine tuning part, like I said, you don't have to fine tune the whole model. You can freeze bottom, let's say X number of layers, and then only fine tune the top few layers, right? And uh, uh, because like I said, the during pre-training, I mean, for the pre-training, if you want to use large amount of text data, the model has to be deep, right? So that is the only reason. And then and during fine tuning, you don't have to fine tune the graphemes section. You just have to fine tune the phoneme parts of the or the fine tuning uses only the phonemes token positions, not the grapheme token position, right? And and like I said, for fine tuning, you can use any or for TTS, you can use any model you want. Just that the encoder should be replaced by this BERT model. And in this case, they are using this NAT paper, which is a recent paper, not recent. I think it's a last year paper. It works really well, and the baselines are from this model itself, and the baselines are already very much competitive to this paper. And the NAT paper has this RNN encoder, which will be replaced by this PnG BERT in this paper. Now let's look at the experimentation. So like I said, for the vocoder, for the TTS engine, they are using NAT for TTS. and they are using wave RNN as the vocoder because the decoder of the NAT model generates spectrogram. You want to convert the spectrogram into some audio, so for that you can use any decoder you want, or sorry, any vocoder you want. There are many varieties of vocoder like IFIGAN, this wave RNN, then then there is something called universal vocoder, and then there are many varieties of vocoders you can use. So, and coming to the PnG BERT model itself, so there are 6 transformer layers with hidden size of 512 and 8 attention heads. And the pre-training, for the pre-training, they use SM3 optimizer with batch size of 24,000 for 1 million steps, and maximum length of the token should be 480 tokens. And only the top 2 transformer layers in the PnG BERT are fine-tuned. Remaining are kept frozen. And performance is evaluated two objectives. One is the naturalness is computed with MOSC score, which is 0 to 5 scale mean opinion score number scalar, and there is a 7 scale side by side preference test, and to compute the subwords, to calculate the subwords, they use a sentence based model with vocabulary of approximately 8,000 tokens. This is the only slide with all the results. There are some ablation studies in the paper. A few more diagrams, you can refer to the paper. The main results are shown in these 3 tables. So first, look at the table 1. So we have this PnG BERT. So this is for the pre-training part. So it measures the token prediction accuracy for 3 different evaluations. So 3 different masking types. One is MLM masking, and the other is G2P masking, which masks out all the graphemes, and the P2G masks out all the phonemes, right? And so if you use PnG BERT without any consistent masking and word alignment, the performance is poor. If you use consistent masking, the performance is good for MLM and uh, uh, and G2P, I mean P2G and G2P. If you don't use word alignment, the performance drops significantly for P2G and G2P, right? As you can see here. So that means the word alignments are crucial in this setting. If you don't use MLM, sorry, if you use only graphemes with MLM, and if you don't want to use phonemes, you're still good. Only if you use word element. If you don't use, then the results are very poor. Okay, this is about the pre-training part, which is good to understand. I mean, this is good to understand because we should know the importance of the inputs or type of inputs you are providing to the model, right? And the second table shows the performance of the TTS models itself, which are the MOS score and SXS baseline. So it's a side by side objective or the evaluation, right? So if you just look at the MOS score, the NAT baseline without any of this BERT pre-training or anything, you're already getting very good MOS score, which is almost close to the humans MOS score or human level MOS score. If you use NAT with PnG BERT, you are getting close to or exactly the ground truth. I mean, it is like 100% accurate MOS score, right? Because this is exactly what uh, human MOS score is, right? So and you can also see, like, if you don't put word element, the performance goes a little bit low. And if you don't do pre-training, then the NAT combining with PnG BERT doesn't do that well because the encoder is not initialized with a good initialization or good weights. And the final table here, as you can see, I mean, this is like in the final table you have both the side by side score and MOS score, and in MOS score you can see that your ground truth performance is as good as, or the NAT with PnG BERT performance is as good as humans MOS score, right, or the ground truth MOS score. This is like amazing, right? and you can't go beyond this. That is the thing. Because if you want to write a new paper, you can't report results which is like more than this, right? Anyway, so that is all about the results, and this is the end of the tutorial. Thank you so much for watching. And if you want to listen to, or if you want to refer to some of the other tutorials, there are many tutorials in my YouTube channel. Please check them out. And if you like this tutorial, please give a thumbs up and subscribe to my YouTube channel. Thank you, and see you all in the next tutorial.